I'm Annette Kirkland, and welcome to Beyond the Gates. In this season, we are talking about leading with innovation.
I'm Carol Coleman, sitting in for Annette Kirkland, and today we're speaking with Dr. Bowen Woodson and Dr. George Kantrales, research civil engineers with ERDC's Geotechnical and Structures Laboratory. And we're going to be speaking about From Blast to Breakthroughs, the tools that test tomorrow's infrastructure. Good morning, and thank you for joining us.
Good morning.
Good morning.
Before we get started, why don't you both tell me about yourselves, your background, and your roles at ERDC?
My name is George Kantrales. I'm a research civil engineer in the structural mechanics branch of GSL. I've been with ERDC for about 3 years. The primary focus of my research here at ERDC is related to blast and weapons effects on structures. Prior to joining ERDC, I worked in private consulting for a few years doing blast-resistant design and conducting research related to blast and weapons effects. And then before that, I was at the University of Florida, where my research focused on vessel impact loading of bridge structures.
Yep, I'm Bowen Woodson. I grew up in Vicksburg, so my dad worked at ERDC in the same building that I work in for 30-something years. So my exposure to blast as an engineer was from a very young age. I just thought that every engineer blew things up. That was all. That's all I thought that they did. So when I went into engineering, that was the path that I always wanted to do. So I started at ERDC as a student in 2015. I converted over to full-time after getting my master's at UC Davis in 2017. And then I'm not quite Dr. Bowen yet. I'm working on my PhD at University of Texas. So hope to finish that in the next couple of years.
That's great.
Very close.
Yeah, getting close.
Okay, well, before we get started, let's get started with some basics. You all test the strength and resilience of structural systems, such as windows, concrete slabs, composite materials, walls, structure panels, connections and joints, the list goes on and on. Why is that important, and what kinds of challenges are we trying to solve?
Yeah, so we rely on these systems, so walls, doors, windows, to protect us from a variety of threats. So both man-made and natural, depending on the use case. To do so confidently and efficiently, we have to understand the performance of all these systems under different conditions and then customize them accordingly. For example, the requirements for something our warfighters rely on for protection from blast and ballistic threats are not the same set of requirements that we would use, for example, for the design of a commercial building to protect its occupants from environmental hazards. In all circumstances, though, it's important that we understand the performance of these systems and leverage testing of the systems themselves or components, critical components of the systems, to make sure that they're providing the protection that we're relying on for the warfighter and the general public, depending on the application.
Okay. And before we get into the dynamic testing, let's talk about ERDC's full-scale water chamber. What is that, and how does it help us?
So ERDC's full-scale water chamber is a very large and rather unique device that we can utilize to evaluate the static resistance. This is kind of your normal non-blast resistance of a structural component through a large range of deformations. It does this by leveraging water pressure. So the pressure behind the wall, the tested component, is increased until you initiate deformation. And once that component starts deforming, the volume, the cavity in the water chamber behind the wall increases correspondingly, which drops the water pressure, dropping the loading on the component. This allows for kind of a slow, controlled failure of that wall through a large range of deformations, which is really advantageous when you're trying to figure out the total capacity or energy dissipation capability of a component. And you compare this to other testing methods that utilize air pressure, for example. They might be good at establishing the stiffness or the overall strength, static strength of a system. But once you get past that peak resistance and into post-peak behavior with large deformations that are typically experienced during blast events or impact events, it does a much less accurate job of that, often initiating premature failure of the component. And so the advantage of the water chamber is our ability to look at the overall resistance of these types of structural systems for a long range of deformations, which is pretty critical during blast and impact when we're expecting these systems to undergo that kind of deformation. We need to understand how they're going to perform once they get there.
Yeah. And I'll add to that too that I mean, we're looking at the capacities of these things, trying to understand how much load can they take and how do they behave. But it's also important just to have this as a mechanism to understand how things fail. Everything's going to fail in a different way. And as a researcher, a lot of times we think we know how things are going to fail, but we don't always know until we test them. So that's kind of what's critical about these. And we have the full scale water chamber here, and that's what's so unique about it is full scale. I mean, it's so large when you put your eyes on it and you walk into our building. It towers over you, and this differs from a lot of other places. And what we also have, which are smaller scale water chambers or small scale ways to test the static resistance of things. So I think that is part of the uniqueness of this. And this is something that, George isn't going to talk about it, but, if we didn't get George 3 years ago, this full-scale water chamber would not be what it is now. We had a project that came in last year, and George really took this thing, which was kind of had been partially built and brought it alive to now it is useful, it is valuable. We can do some testing in there, and he did some validation testing in that last year. So it's a good thing that we have and we can use to move forward and test now all kinds of structural systems, whether it be walls with cutouts for windows, CMU walls, concrete walls, whatever it may be. Now we have that as an option for us moving forward.
So I understand that before testing how a structure moves, we first need to understand how it stands still. Why is that so important?
So there are a couple reasons for that. First and foremost, when you're talking about the way that you conduct research, you typically start with a fundamental understanding of behavior and then push outward from there. If you skip steps and you test everything at once, you'll have a hard time distinguishing which characteristics are affecting which outcomes. It's not a very thorough approach. So it kind of limits the applicability of what you're able to generate through your testing. The second reason, more practically, if you're trying to develop an engineering model for a physical response, that model needs to capture every aspect of the behavior. And so structural systems, as they respond statically, have a certain component of resistance. When you move into the world of dynamics, and then additional terms or facets are added to that resistance. So by breaking them into their parts and pieces, understanding each piece and then assembling things together, you get a more comprehensive and robust way of understanding and evaluating a structural system response that allows you to take your model and go outside the bounds of what you have utilized for your testing and more confidently understand that what you're generating should be at least reasonably valid. This is in comparison to something that's just, if you have a model that's direct fitted off of test data and you try to extrapolate that without understanding what you've generated, you could be pretty wrong when you get outside the bounds of your testing. And this can provide, potential issues when you're developing protective systems based off of those models to protect the general public or the warfighter from different types of threats. You want to have a lot of confidence that what you're predicting is in fact correct. And so relying on a firm understanding of the fundamental behaviors, starting with statics first, is the proper way of doing that.
Okay, now let's talk about ERDC's 200 kip dynamic loader. How does this machine stimulate real-world forces, and what types of structures or materials do you test with it?
So ERDC's 200 kip dynamic loader is a rather unique device that we utilize to test the static and dynamic capacities of different types of components and connections. It operates by utilizing pressurized fluid in two chambers above and below a piston. You can increase the pressure in each of the chambers to kind of control the load rate to a certain extent. But you drain the fluid from the bottom chamber, which initiates downward motion of the piston and then loads the component correspondingly. So like I said, you can modify the pressure in the chambers. You can change the rate at which the fluid is drained from the bottom chamber to control the load rate very carefully. You can do this from static all the way to very rapidly dynamic load rates. So it's a very flexible device. We've used this in the past to test many different types of components and connections, concrete anchors, steel reinforcing bar couplers, structural steel bolted connections and screw connections. So the range of components we've looked at already with this device are pretty substantial, and it's added quite a bit of value to the research that we've been able to generate.
And I also understand that the dynamic loader can be set up in different configurations. How does that flexibility improve the way we test and understand structural performance?
Yeah, so I should mention that the 200 kip loader is so named because it's capable of generating up to 200,000 pounds of force in less than 2 milliseconds.
Wow.
Very rapid. And so, that is part of its flexibility. We can test very small things to very large things, very slow quasi-static load rates up to very rapid load rates as well. Adding to that flexibility, we can reconfigure the loader to test different types of loading conditions. So structures experience different types of loads, tension, compression, shear, flexure. And to kind of confidently understand that the capacities you're generating from your connections sort of replicate the loading conditions they would experience in service, you have to test them under those different conditions. And so you can reconfigure the loader to simulate tension, compression, flexure, if that's the response mode of interest, quantify how those capacities change under those different circumstances, and more comprehensively provide feedback regarding what the resistance of those connections would be. And so, like you have concrete anchors and shear will behave differently than in tension or a combination of shear and tension. In some cases, the capacities will be lower, depending on what load combinations you're evaluating. So it's rather important to be able to have that understanding comprehensively of what your resistance is.
Okay. And a big concern in structural integrity is how connections hold up under extreme forces, such as hurricanes and tornado winds, shock vibration, earthquakes, impact loads, and explosions. How does this dynamic loader help identify weak points in these connections?
Yeah, so connections are a common point of failure in structures, even in conventional construction. It's all the way from earthquakes to blast loading, anything dynamic in particular. That's going to be most likely where you're going to experience initial failure. Also, interestingly enough, as you transition from static to dynamic loading conditions, the capacities of your connections change, and sometimes the failure modes change as well. So if you base your understanding simply off of static testing, when you're trying to design something to protect the warfighter, for example, from blast threat, you will be potentially wrong. In some cases, you may be underestimating the capacity because dynamic loads under certain conditions can increase the capacity of a connection. That's called a strain rate effect in most cases, or a load rate effect. However, in other cases, the capacity can be potentially reduced or the failure mode can change, leading to a more brittle or premature failure of the connection, which overall could have the effect of reducing the effectiveness of your structural system. And so utilizing the loader or a similar dynamic testing device, you can look at how that capacity changes and the failure mode changes from the very slow rate static tests all the way up to the very rapid experiments indicative of blast loading. And you can understand that comprehensively. So for different use cases, if you're looking at something that could withstand loads from a very rapid event, you could have an understanding of what that connection could sustain relative to something that might experience quasi-static load only, or a combination of quasi-static and maybe very slow rate dynamic loads. So having a comprehensive understanding over that range is rather important when you're designing connections.
And connections are something that we can always evaluate at full scale in the field. We have explosive test ranges that we can go test that, and we can build our specimens and test the connection in the field. And that's very expensive and time consuming. So one of the huge advantages of the dynamic loader is, I don't know, George, how many tests in this last test series could you do a week on the dynamic loader?
Oh man. I mean, if you got 15 tests a week, and that's with components that are decent sized, not massive, but you can get off 3-4 tests a day. And the advantage of the loader, extending beyond just simply field testing, is it's very controlled. You don't have as much concern about breaking your instrumentation, for example, if you're trying to record information. If you do miss data replicating a test a second time if you need to gather that data. So controlling the environment when you're looking at something as intricate as a connection is rather important. The field testing or shock tube testing, as we'll talk about in a little bit, have their place in terms of understanding overall system performance. But as you're building up to that system performance, kind of looking at the individual small building blocks, it's very helpful to do that in a controlled environment. And like I mentioned before, the number of different types of loading conditions and circumstances that connections can find themselves in necessitates a pretty significant matrix of tests to kind of flesh out what that capacity is and how it changes. And that means you have to do a lot of tests relatively rapidly to try to remain efficient so that your testing program's costs don't just skyrocket.
Moving from controlled lab testing to real-world scenarios, ERDC has a blast load simulator. What does this facility do?
So ERDC's blast load simulator, the facility itself is the blast load simulator or BLS facility. We have several shock tubes there. They're ranging from a smaller shock tube, 4x4 foot specimens, to a very large advanced blast load simulator, which can fit 12 foot by 12 foot full scale specimens in there. It's called a blast load simulator because it simulates shock loading indicative of explosive event utilizing either compressed gas or detonating a combustible gas, as opposed to, for example, in a field experiment, you would detonate an actual explosive charge in an open field to initiate the loading. Some of the advantages of the blast load simulator facility itself are that you can do in a relatively controlled environment, similar to the dynamic loader or the water chamber, a number of tests to evaluate the efficacy of a prototype system under dynamic loading conditions. So if you've done your research appropriately and you've evaluated static capacity, you've looked at connection performance, and now you're moving up into a prototyping stage, the BLS facility allows you to do that and subject that structural system now, to a bunch of different types of loads, depending on, again, the use case for that system. And so, once you're able to do that, it allows you to modify, if you, for example, discover during the course of that testing a design change that needs to be made, or an improvement, perhaps, an adjustment. You can make all those tweaks, during your shock tube testing program, or you can evaluate an array of different potential designs, for example, that you designed in advance and then evaluate in the shock tube, and then make a final determination on what the basic characteristics of your prototype protective system are before you move into field testing or larger scale experimentation, such as a demonstration event, which can be a bit more expensive, more sizable, but also allow you to represent the blast scenario a bit more accurately, or perhaps the boundary conditions a bit more extensively. For example, if you're looking at the response of a small building, for example, instead of just a wall, if you want to do a field test, you can do that whole system. But it's helpful to look at it on a prototype scale first, and that's what the BLS facility allows us to do.
Why is it so important to test structures at full scale rather than just relying on small scale models? And what are the advantages? What other advantages do full scale model testing offer?
So I guess now we can kind of take a step back and look at all of these things that George has been talking about from a more comprehensive view. We have all these things, including our small water chamber, our full scale water chamber. We have our dynamic loader. We have the BLS facility. So, the next step in this, after being in the controlled environment, if you haven't already validated everything that needs to be validated, is you can move out and do, full-scale testing. So there are some parameters that are really difficult to understand, at small scales. There's things that we can't scale. So without the use of a centrifuge, which GSL also has one of those too, but it's hard to scale, gravity, for example. Gravity on Earth is what gravity is on Earth. So that's something then when you're working at small scales, you can scale the standoff of your charge, or you can scale the blast basically through standoff and the charge weight. You can scale geometry. You can scale geometry of your target. But gravity is a hard parameter to scale. Or, if you're talking about concrete, for example, and you want to test a concrete wall, it's hard to scale the aggregates inside the concrete, that make that concrete mix what it is. So you can scale certain parameters of those, but still it is important to test at full scale to validate everything that you have done up to this point. So one thing we often do is we would test, for example, on our small scale water chamber, and then we would pair that with some numerical modeling. So we can validate our numerical model, at the small scale. And now we can exercise and run through a lot of different scenarios. But how do we know that when we move up to the next level that our model is still accurate at full scale? Well, that's when we can then pick, one or two scenarios, and we can validate, at full scale, whether that's statically at our full scale water chamber or dynamically with our ABLS or out in the field. So it's important, just for us to have that as a gut check and as a validation point to ensure that everything and all the science that we've done up to that point is accurate.
Okay. And how do all of these testing methods, from water chamber to dynamic loader and the blast simulator, how do they work together to give a complete picture of structural performance? At the end of the day, what's the impact of this research?
Yeah, so I guess the first part of that question is what I started to answer previously, and how they work together and how we can pair them. And George did a good job of describing each of those. For example, there are limitations if you're wanting to look specifically at connections and you go out in the full scale. There's aspects of that structural system as a whole that will influence the connection instead of isolating that connection alone. So, like I said, we can systematically move through this process of small scale water chamber, full scale water chamber, dynamic loader, BLS, and then sometimes we have to go out to explosive ranges because something is either so big or it's a loading condition that we cannot replicate anywhere else. So that's how all of these things kind of work together to validate the structural performance or to investigate the structural performance of something. Why is this important? I guess we've been talking about all of these things, but everything that we do on the weapons effects side is in support of the Army or other government organizations that have a need, and they come to us. And one of the reasons they come to us is because of our unique facilities and because of our people like George. I think it's the primary reason that they come to us.
Bowen is selling himself short here, I think.
We have people that are world experts in this field. They spend their career deep diving into these things. So for the Army, if there is a certain protective technology or an element that will protect the warfighter that we need to investigate, and we can develop these technologies, or we can validate existing structural systems, we can do that. Other government organizations may be interested in doing the same thing. If you think about U.S. Department of State, Department of Homeland Security, those types of organizations that are also very interested in protecting both on the military side and on the civilian side of things. So, the work that we're doing, it is directly feeding into protecting civilians and the warfighter, and that's everything that we do and the impact of our work. That's why I think that we get so excited about our job, is because we know that the things that we're doing, they're fun while we're doing them. We enjoy what we're doing, but ultimately, like the people in GSL and the people at ERDC, if you're not buying into the impact, then these people may choose to go work somewhere else, right? But the people that we have, that's what they care about, right? That's what everything leads to, is the impact of the work and who we're protecting.
And that's the main motivating factor that drives all of us. So, building on what Bowen said, everything we're doing, everything we're trying to do with these facilities is to protect people, especially the warfighter and folks in support of the Army. And that's what motivates us to use these facilities, develop these facilities, and to come work here. That was my motivating factor for coming here from the private sector, was to devote all my attentions directly on the things that matter most to me and our nation.
Excellent. Absolutely excellent.
I'm Annette Kirkland. Beyond the Gates continues in a moment. You're listening to News Talk 107.7.
When you walk into convenience stores in our area or in Louisiana, Arkansas, Tennessee, or throughout Mississippi, chances are you'll find many products distributed by Vicksburg Specialty Company. Vicksburg Specialty Company has served convenience stores since their opening in 1936 by the Nassif family. Their business is now in the Nassif family's 4th generation of operation. A Vicksburg company that brings our area to many areas throughout the Southeast. Vicksburg Specialty Company.
Welcome back to Beyond the Gates. You're listening to News Talk 107.7.
If you're just tuning in, I'm Carol Coleman, and I'm sitting in for Annette Kirkland today, and I'm speaking with Bowen Woodson and Dr. George Kantrales, and they're research civil engineers with ERDC's Geotechnical and Structures Laboratory. And we're talking about from blast to breakthroughs, the tools that test tomorrow's infrastructure. So kind of wrapping it up, looking ahead, are there any key takeaways that you'd like our listeners to understand about these testing capabilities?
Yeah, I think that, we do a lot of really cool stuff at ERDC. We do a lot of really cool stuff at GSL. And, without things like this, people in the community don't really, know about all of these, cool things that we're doing. But we have some really powerful facilities, some really powerful techniques that we have just, right here in Vicksburg that are heavily influencing the protection of the warfighter and protection of civilians, against various types of threats. And it's using these facilities that we have that are so unique to us, that anywhere else in the world, these people do not have this set of facilities to get to do what we do, to walk through the entire process, starting statically at small scale, statically at full scale, dynamically isolating things like connections, in controlled environments, doing testing like we do in the BLS, explosive testing, and then the access that we have to explosive test ranges to do full validations of these things. It's extremely unique, it's extremely powerful, it's really impactful, and then all of it's happening right in GSL in Vicksburg.
Mm-hmm. Do you have anything to add, George?
No. Bowen pretty much hit the nail on the head there. I think when you're talking about the full range of capabilities afforded to a testing agency, particularly as it pertains to looking at the dynamic response of structural systems, we're looking at blast resistance in particular. ERDC's pretty unmatched in terms of what we're able to do and the problems we're able to solve. And if anything looks out of place, how we're able to dial down to the specific aspect of the system that looks a little strange and comprehend why that behavior is occurring. And we can do that in the laboratory setting. We can do that out in the field. We have the staff knowledgeable in the response of these systems and experienced to be able to make determinations that our government relies on to protect people. And that's the main takeaway that I'd like people to have is that we have the capabilities, we have the knowledge, and we have the desire, and it is a burning desire to protect the people and our warfighter.
The U.S. Army Engineer Research and Development Center, or ERDC, is the premier research and development center for the U.S. Army Corps of Engineers. Hello, I'm Carol Coleman, and I would like to share with you how ERDC makes the difference. Established in 1998, the ERDC is home to more than $1 billion worth of world-class facilities located in 7 laboratories and multiple field sites across the country. The organization's main campus is situated on the historic Waterways Experiment Station in Vicksburg, Mississippi, and consists of the Coastal and Hydraulics Laboratory, the Environmental Laboratory, the Geotechnical and Structures Laboratory, and the Information Technology Laboratory. ERDC also operates 3 laboratories not located on the West Campus, including the Construction Engineering Research Laboratory in Champaign, Illinois, the Cold Regions Research and Engineering Laboratory in Hanover, New Hampshire, and the Geospatial Research Laboratory in Alexandria, Virginia. Each laboratory has their own unique mission and operates as integrated teams of engineers and scientists to address a broad range of science and technology issues. The Coastal and Hydraulics Laboratory, or CHL, addresses an entire spectrum of water resource challenges. Their mission is to deliver solutions to our nation's most challenging coastal and hydraulics problems. As part of the CHL, the Field Research Facility, or FRF, is a U.S. Army Corps of Engineers field site located in Duck, North Carolina. The cornerstone of the FRF's contribution to coastal research has been its long-term data measurements that stretch back to 1977. The long-term measurements have made the property one of the best studied beaches in the world. Providing solutions for tomorrow's environmental challenges, the Environmental Laboratory, or EL, is ERDC's primary center for ecosystem science, ecosystem technology, and environmental resiliency research. The laboratory is home to the Aquatic and Wetlands Ecosystem Research and Development Center and the Hazardous Waste Research Center. ERDC's Geotechnical and Structures Laboratory, or GSL, supports our nation's defense, security, public safety, and infrastructure. GSL is home to the world's largest heavy vehicle simulator, the Centrifuge Research Facility, and the Advanced Blast Load Simulator. In today's fast-paced digital environment, the Information Technology Laboratory, or ITL, provides innovative solutions to solve the nation's most complex and challenging IT and computational issues. The laboratory's Supercomputing Resource Center is one of only 5 Department of Defense computing centers operated by the DoD High Performance Computing Modernization Program. For more than 50 years, ERDC's Construction Engineering Research Laboratory, or CERL, has supported the Army's ability to design, build, operate, and maintain its installations and contingency bases. Located in Champaign, Illinois, the laboratory is home to the Triaxial Earthquake and Shock Simulator. ERDC's Cold Regions Research and Engineering Laboratory, or CREL, delivers environmentally relevant and transformative engineering solutions to test, evaluate, and improve infrastructure and equipment, particularly for use in cold regions. Located in Hanover, New Hampshire, the laboratory is home to the Frost Effects Research Facility, the largest refrigerated warehouse in the United States. The Permafrost Tunnel Research Facility is a U.S. Army Corps of Engineers field site operated and maintained by ERDC's CREL. The tunnel, located just outside Fairbanks, Alaska, is a unique natural research facility with features up to 40,000 years old. ERDC's Geospatial Research Laboratory, or GRL, located in Alexandria, Virginia, serves as the Geospatial Research and Development Laboratory of the U.S. Army Corps of Engineers. GRL is the only dedicated geospatial research and development laboratory in the entire Department of Defense. As the premier research and development center for the U.S. Army Corps of Engineers, ERDC has unique, world-class equipment and facilities.